All right, everyone. So I'm going to be reviewing Lab 6, which was on lenses. So, as a reminder, the first part of the lab just tells you that if you put light going in any direction through a flat pane of glass, it will just remain going in the same direction that it went before. And then the next part of the lab just talks about what a converging lens is versus a diverging lens is. So when you put in parallel light through a converging lens, um, what you'll see is the light converging here. And then for a diverging lens, for a converging lens, if you come out of the focal point at an angle, you'll get parallel light. And then for a diverging lens, it's the opposite, where you put light in and it diverges away from the focal points. And then if you put it in at an angle, it'll come out parallel. It's not just like any angle; it has to be the same angle that it would come out if you were to put the light in parallel. And then the lab talks about what the different types of parallel, or not parallel, the different principal rays are, but I'll talk more about that. And then they give you this expression, which they call the thin lens equation, where this S is the object distance, this S prime is the image distance, and this F is the focal point of the lens you're using. And then I think that the knowledge in this box is something you should put down in your lab notebook or memorize, possibly both. I think it's helpful. And then the magnification of an image is just h prime over h, or it's negative s prime over s. And then it walks through like a two lens example, which I think is helpful, and I think you should read through it. But getting on to like stuff that we can actually solve. So we have a converging lens here, and we're far away from f. This far away is like kind of means that like you're greater than 2f away, but you could interpret it either way. So if you're greater than 2f away, then this image over here will be diminished. And so really quickly, the how I made this was this first principal ray comes parallel to the object, and then once it hits the converging lens, it goes through the focal point, and then the second principal ray will go straight through the center of the lens here, and then the third principal ray will go will not go parallel, will go through the near focal point, and then once it hits the converging lens, it will go parallel. All right, and then where these lines meet up, you will have an image formed. All right, and so we can see that this image is diminished, and then it also is not erect, it's upside down, which I'll call U. So it's diminished, upside down, and then, sorry, what was the last thing? And it's a real image because these are real rays, okay? So it's diminished, upside down, and it's real. And then we do the same thing for this one, and we can see that this time it's magnified, but it's also upside down and real. So I'll say magnified, upside down, and real. And then we can do the same thing for this one. But here we see that like even if we were to draw virtual rays, they'll never actually meet up, which means that we have no image. And so if we have no image, then it can't be magnified, or so it can't be magnified or upside down or erect, and it also can't be real or virtual. And then for D, we see that like the lines don't meet over here, but if we were to draw rays backwards coming out of these two lines, then we would see they would meet up here. And so these are virtual rays. These green rays are virtual, and then where the green rays meet, we draw an image, and we can see that this image is magnified, it's erect, and it is a virtual image. Okay, then we do the same thing for this one. we see that this time it's in front of the focal point, but that doesn't really change anything. Like it's still magnified, erect, and a virtual image. All right, and so the answer is 1.2 through 1.4. Now 1.5, we do the same thing with diverging rays, except for the first principal ray. So again, it comes parallel out from the object, but once it hits this, once it hits the diverging lens, it goes at an angle such that if you were to draw the line back, it would go through the near focal point here. And then the second principal ray, again, just goes through the center here. And then the third principal ray goes through, it goes essentially on a line through the far focal point, except when it hits the diverging lens, it goes parallel. And so again, when all three meet, here there's only 2 green, but like theoretically you could act as if this was like, I know this is a real ray, but like if you were to extend backwards from here, you would have 3 green, but you really only need 2. So this is our virtual image. We can see it's diminished, erect, and it is virtual. Then we do the same thing for this one, and again it is diminished, erect, and virtual. And then we do the same thing for this one, and again it is diminished, erect, and virtual. And you'll notice that before, when we had an object on the focal point, we couldn't get an image, but if we have a diverging lens, then you actually do get an image. And it's right there. And then here we have it's diminished, erect, and virtual again. And then the last one, again, it is diminished, erect, and virtual. So all of them for the diverging lens were diminished, erect, and virtual. All right. And so then the next part of the lab, like the next 3 parts of the lab are like pretty much all experimental, but I wanted to go over one example of like calculating the object distance and image distance for a given like focal point or a given lens. So in the first example, you have a 100 millimeter focal length lens and it's converging. And then we have a 1 meter, like the screen is 1 meter away from the light source. Okay. And so essentially what that means, or the important part of that, is that s plus s prime is equal to 1. And this implies that like s prime is just equal to 1 minus s. And so if we plug that into our thin lens equation, which is 1 over s plus 1 over s prime equals 1 over f, we have 1 over s plus 1 over, and then also the focal length here is 100 millimeters, which equals 0.1 meters. All right. Plus 1 over 1 minus s here, because here I'm replacing s prime with 1 minus s, which we found there, and then 1 over 0.1. And then that means that we have 1 over s plus 1 over 1 minus s equals 10. And then we can multiply 1 minus s to both sides of the equation to find that 1 minus s over s plus 1 equals 10 minus 10s. And then we can multiply s to both sides of the equation to find that 1 minus s plus s equals 10s equals 10s minus 10s squared. And then here, these two s's cancel out. We can bring this 10s squared to the other side, and here also to the other side, and we have 10s squared minus 10s plus 1 equals 0. And then if you were to solve this equation, it might be easier to write it as like s squared minus s plus 1 over 10 equals 0. But if you were to solve that, then you would find that s has 2 possible values, which are 0.113 or s equals 0.887. Okay. And then essentially, so these would be in meters since we wrote the focal length in meters before, and we also wrote S and S prime in meters here. But regardless, we have S equals this, S equals these two possible values, which means like here S prime would equal to 1 minus this, which would be 0.887. And then S prime here would be 0.113. And so essentially what that means is that our possible magnifications are negative 0.887, 0.887 over 0.113 equals negative 7.85, or the other possible magnification we have is negative 0.113 over 0.887, which is just 1 over the negative 7.85, which would be negative 0.127. And so this is what pretty much everyone found in their when they did the lab, like in their reports. But so hopefully that example made sense. But again, the rest of the lab was like all experimental, and there weren't really questions at the end. So I won't talk about that. But hopefully, going through the drawings of the ray diagrams and stuff was helpful. But thank you.